Hello, everyone. Thank you for joining today's session. Today we are talking about the geospatial data engineering and analysis on Databricks. At the end of October, the Unifeye team had the opportunity to participate in a one-day workshop at the Databricks London office, focused entirely onto the geospatial data. It was an incredible, insightful session. It brings together Databricks architects and partners. And following that workshop, we decided to bring those highlights and discussions to a wider audience, to all of you, the Databricks practitioners. In today's webinar, we are going to cover the fundamentals of geospatial data engineering on Databricks, how to manage, process, and optimize the spatial data sets at scale, the key database capabilities that make this possible, from Spatial SQL, and we will see those, to Unity catalog and integration and the Lakeflow orchestration as well. We also have real-world use cases, how you can use the geospatial data, and we have not one but two demos. So let's get started. Let's meet our host today. So I'm Bianca, I'm the Chief Data Officer at Unifeye. Today we have as a special guest Josh Brahma, which is a solution architect at Databricks. And also from the Unifeye team, we have Jordan and Hasnat, who are our two senior data engineers. Just a quick word about Unifeye. We are proud to be both a Databricks partner and the organizer behind this user group. At Unifeye, we focus 100% on Databricks. Everything we do is around helping organizations to get faster value from the Lakehouse platform. We build accelerators, training programs, managed service that simplify complex data and AI transformations. So from the Unity catalog deployments and to the Delta Live tables pipelines. Actually, Lakeflow declarative pipelines, sorry, I'm not getting used to call them in this way, to the AI analytics. Our goal is quite simple: to make the data engineering, the governance, and the AI adoption faster and more accessible, not only to the data engineers, but to the wider business. And today's session, we are going to highlight how geospatial data is going to do that as well. So, why geospatial data and why Databricks? Let's start with the why. Every organization today has some sort of element of location data, whatever it is: store addresses, customer postcodes, delivery routes, sensor coordinates, or service areas. In fact, over 80% of enterprise data contains a spatial component. But the challenge is that most of this data sits in silos, managed separately into geospatial information system tools, spreadsheets, or legacy systems, and they are completely disconnected from the rest of the analytical ecosystem. That means the insights are fragmented. You can easily access and combine the spatial patterns with customer behavior, financial performance, or operational KPIs, which are quite important for the business side. And this is where Databricks changes the game. By bringing the geospatial processing directly into the Lakehouse, Databricks allows you to work with spatial and business data together in one government scalable environment. You can now join geospatial data sets with the sales, logistic, or demographic data just using SQL, all governed by Unity catalog. So instead of data scientists or analysts needing special geospatial systems, software packages, your entire team, data team, can now operationalize the geospatial analytics as part of your broader data and AI strategy. From a business perspective, this unlocks use cases such as retail site optimization by choosing the right location based on customer density. Supply chain optimization, you can calculate the routes, the catchments, and delivery zones dynamically. And into the public sector, In sustainability, you can map the areas of needs, risk, or environmental impact scale. So that's the foundation why geospatial matters and why database is quite uniquely positioned to make this practical, scalable, and collaborative. When we talk about geospatial data, it's easy to think only about maps, but in reality, almost every data set has a spatial component. If you look at the examples on this slide, you will see how broad the applications are. So if we look on the left side in front end abuse detection, location partners can reveal unusual activities such as multiple insurance claims filed from the same region or repeated transactions at unexpected places. In retail, the geospatial analytics drives site location, store performance, and footfall analysis, helping brands decide where to open their next location and how to plan campaigns. In financial services, the spatial data supports loan risk assessment and economic distribution mapping, understanding the link between geographical data and customer risk profiles. If we look onto the right side upper, in healthcare, it's used to identify diseases, epicenters, understand in the environmental impacts, and plan the public health interventions. We saw most of the scenario during COVID. Finally, infrastructure and energy rely heavily on spatial data for transportation planning, agriculture management, climate modeling, and asset inspection. In short, anything that has latitude and longitude coordinates can be considered geospatial data. That means that whatever you are tracking, delivery routes, sensor readings, customer location, or power grids, you already have geospatial data. The challenge is making it usable and actionable at scale, and that's exactly where Databricks helps. It takes these traditionally heavy geospatial information systems bound data sets and make them part of your everyday analytics. It's fast, it's collaborative, and ready for AI. So, if geospatial data is everywhere, why isn't everyone fully using it? This is the question that we are going to answer today. So the short answer is scale, but let's look at the three main challenges. First, we are dealing with increasing amounts of rich data. Thanks to mobile devices, satellites, and IoT sensors, acquiring spatial data has become easier and far more cost-effective. Every photo, drone scan, or vehicle movement adds another layer of geospatial information. But the challenge is that this data arise in massive volumes and at a high velocity, and most organizations simply aren't equipped to manage or process this efficiently. Second, we rely heavily on legacy data formats. Many geospatial data sets are stored in outdated or inconsistent file types, and that don't integrate well with modern analytics platforms. Indexing and coordinate handling often becomes the bottlenecks, and moving between different tools eventually means conversion, data loss, or duplication. And third, traditional geospatial systems tools, while are powerful for analysis and visualization, were never designed for large-scale processing or collaboration. They are great when you are a single analyst exploring a small area, but not when you are a data team trying to process billions of coordinates across multiple regions or join geospatial data with other business data sets. That's where many organizations hit the wall. The tools don't scale, the formats don't align, and the data grows faster than the infrastructure can handle. Beyond the data size and tool limitation, there are two other challenges that really slow down the geospatial work: pipelining and advanced analytics. So let's start with the pipelining. A typical geospatial workflow involves
I'm sorry, Bianca, I think we've lost you. We can't hear you anymore.
from one to another, and every data set adds risks. Is there a question? Sorry.
Your mic cut out for a while, but you're back. I think that's it.
Which part?
Just for quite a bit of the slide.
Do the pipelining. Should I will retake it. That's right. So,
yeah.
what I was saying that two other challenges that really slow down the geospatial work are the pipelining and advanced analytics. You have in front of you a typical geospatial workflow, and many times involves a lot of interdependent steps, things like georeferencing, alignment, image correction, object detection. The problem is that these steps often require different tools, libraries, or systems. And what happens is that your data moves from a format to another, from a system to another, and becomes inconsistent. And every transfer, it's adding a risk of delay, data loss, or inconsistent results. All of these tools need to talk to each other in a timely and reliable way, and sometimes it's not the case it's very rarely in the reality to be the case. Now on to the advanced analytics. So there is a big gap between spatial analysis and AI, and this is where platforms like Databricks come in. Onto the advanced analytics side, most of the traditional geospatial information systems tool, they were never designed actually for machine learning and AI workloads. They are excellent for mapping and visualization, but when you want to do something predictive like detecting changes in land use from satellite images or clustering customer movement patterns, you quickly hit their limits. And this is the gap that Databricks is going to fill in. So this is the point where the geospatial stops. It's stopping to be a niche capability, and it is becoming integrated part of your data and AI strategy with Databricks. I'm handing over now to Jordan. On to the next slide.
Thank you very much, Bianca. Yeah, next, there we go. Thank you. Okay, so why is Databricks then a suitable platform for working with geospatial data? Well, the first thing to say would be to address that challenge that Bianca has been talking about, the challenge of scale. Given the amount of geospatial data that is produced nowadays, we need somewhere or something that can process big data effectively, and that makes Databricks really the natural choice as a highly optimized platform for handling big data with Spark and distributed computing. Bianca did mention some other challenges as well, such as inefficient storage, indexing, and coordinate reference system challenges. And I'm going to look into those a bit more in the slides to come. But before that, I just want to mention that Databricks, of course, is much more than just like an engine for efficiently processing data, although that's like a big strength. With the Lakehouse, you can bring your geospatial data in from wherever it is in whatever format. You can clean it, transform it, make it available for your typical business intelligence use cases. And also a great aspect of Databricks is all the machine learning and AI system side. So you can do a lot with your data in Databricks. So we know it can handle the scale of the data. I want to go into more detail on how the data itself can be challenging to work with. So if we move on to the next slide, please, Bianca. Right. And then the text as well. There we go. Can't remember how many animations there are, but maybe one more. Yeah, okay, good. That was good. So yeah, coordinate reference systems, we mentioned those. What are they? Well, the idea is that they are simply a way to map every location on Earth with a set of coordinates. They'll be quite familiar. You get geographic coordinate systems, which describe locations using spherical coordinates. And these are most commonly shown in degrees of longitude first, longitude and latitude. The second type is your Cartesian coordinates or projected coordinate systems, which describe locations using Cartesian coordinates like X, Y, and maybe Z. That's all fine. That's quite straightforward. The problem is that there are thousands of coordinate reference systems out there. For example, in the UK, the most common one is the British National Grid. But of course, if you have data from another country, it's just not going to be the same. It's not going to have the same reference. So converting between them is an important thing that we have to be able to do. And Databricks helps us with that, with some of the functions that are now available, which I'll show in the final part of the presentation. But for now, I just want to keep talking about some more of the challenges. So I'll go on to the next slide, please. Thank you. Around some of the tasks that you might have to complete with geospatial data. There's quite a few that might sound quite simple when you first conceive of it, but in practice, they become quite complicated. So one typical problem or one typical task that you might have to perform is you have points and you have some polygons, and you want to know if the points are inside the polygons. And it doesn't sound too complicated at first, but then you try and figure out like how does it actually work. Well, this task really is like it's a spatial join or a point and polygon join, and the typical way to tackle it is with a ray casting algorithm, which is what you can see on the right hand side. Basically, what it involves is drawing a line. It could be in any direction, but in this diagram to the right, from the point out, and then you count how many times it crosses an edge of the polygon. Simple in theory, but it's actually, well, the complexity is polynomial and scales with the number of points and number of polygons and the number of segments of the polygon. So if you have a lot of points and a lot of polygons and a lot of segments, then performing this spatial join can become quite a big problem pretty fast. So we need better ways more efficient ways of solving these problems, which we'll see soon. So yeah, the next slide is about spatial indexing. So this is really about how we can simplify working with spatial data. Just like regular indexing on regular database tables, we want to be able to speed up how we read data. We don't have to read all the rows. And there are several spatial indexing techniques out there, but the one that we're showing here is H3, which was developed by Uber. So it's a hierarchical hexagonal geospatial grid system, and it's shown there on the right. And basically what it is it's made up of layers of hexagons. So at the top level, you've got quite a coarse, well, very coarse set of hexagons, and then they have children, which have children, which have children, which have children, for about 16 layers. So you go at the very finest level to about a resolution of around a meter squared, a little less. Yeah, so in H3, one of the ways that we can make it quite efficient is that locations or cells have very similar IDs, which allows data to be co-located. Like in Delta Lake, we have the power of optimize and Z ordering. So if we optimize on that column, then we can make the data co-located, and through data skipping algorithms, we can dramatically reduce the amount of data that actually needs to be read during queries. And Databricks has over 30 built-in functions now for working with H3. So working with this data is easier than ever. These functions include indexing data from standard formats, performing aggregation within the cells, efficient joins and traversal around the hierarchy. And it's worth pointing out that, yeah, there's other implementations of H3 in other places, but it's particularly performant on Databricks, as these functions are all photonized. So like Photon is Databricks' engine for running fast and cheap queries. So yeah, these functions perform very well. Next slide, please, Bianca. Thank you. And finally, just getting on to the last piece is around Spatial SQL. So recently, one more click, I think, Bianca, please. Yeah, the Spatial SQL is a new addition in Databricks. Essentially, it introduces two new things, or two new categories of things. We have new data types, and we have new functions. So the data types are the geography and geometry data types. And essentially they represent similar things, like they represent points, lines, and polygons. But geography uses spherical coordinates like longitude and latitude, and geometry uses your X, Y, Z Euclidean coordinates. The geospatial functions are here as well to help us work with these data types. So you can import and export. So like if you have a representation of a location, you can convert it to like a geography or geometry type and vice versa. And you can also take measurements, like how far away is this point from this polygon, or and in relationships as well. So you see like contains there. That's a kind of example of how we would perform that spatial join from before, where we want to tell if a point is in a polygon. It's actually very simple on Databricks with these new Spatial SQL functions. And there's many more, of course, which are also all photonized, so all very performant as well on Databricks. So with all that, we want to emphasize that Databricks is now better than ever for working with spatial data. And with that, I'll hand over to Josh, who's going to give us a bit of a demo.
Thanks, Jordan. Yeah, so hopefully I can bring some of these concepts around spatial and spatial data and spatial queries to life by showing you what this looks like in some Databricks notebooks. So I'm going to jump into my Databricks workspace. Hopefully you can see my screen. Just give me a shout out if that's visible.
Yes. Yes.
Yeah, fantastic. Okay, so I'm here in my Databricks workspace. I'm going to run through a few notebooks. The first notebook is going to read in some automatic information system maritime vessel data, location data. And this is actually an open source data set. And after this, I'll share the GitHub repo where you can actually run all of this stuff end to end, including downloading the data. So all of this is entirely reproducible. And I'll share information on that at the end. So first of all, I'm installing some Python libraries. And then I'm going to specify some catalog variables. So catalogs are kind of high-level objects in Databricks for working with data. And we have a catalog called Unity catalog, which enables you to work directly with files in this case, in something called a volume. So I'm reading my raw AIS CSV data, and I'm using Python to interact with that. And you see, like, my notebook is set to Python. You can use SQL as well, and you can kind of swap between those in Databricks. So I read in my my CSV file, and in this case, I'm just reading one file, but I could be reading, many files directly from Cloud Object Storage. And I'm going to load that using Spark and just take a quick look at my data. And this is what AIS data schema looks like. We have some unique identifiers. Latitude and longitude are the spatial elements that we're particularly interested in. And that's, a printout of my data frame. You notice we have vessel names in there, which is quite a handy bit of metadata. So first of all, I'll just look at all the other data types and do a quick sense check of what's there. And I can look at the missing fields and all that kind of stuff, like standard EDA type stuff. Then I'll do a quick count of how many unique vessels using the MMSI, which is a unique identifier. So I've got 16,000 vessels in my vessel location data. And I'll look at the geographic bounds as well. Like, what's the bounding box coverage of my data? What's the spatial coverage? And I can just do a min-max of the latitude and longitude, right, to get a box. And then maybe I'll plot that on a map. Now, this is actually quite misleading, this visualization, because it's giving you the min-max all the way around. But because our data traverses the international date line, it appears that this data set covers the whole world. But in actual fact, as you'll see in a minute, the data is focused around North America and the coastlines around that. So let's create a delta table. And as we've discussed already, Delta Lake is a capability in Databricks. It's actually open sourced by Databricks as well. That allows you to work with files in object storage directly, as if it was a SQL database. So that's probably the best way of explaining it. So I'm going to use Spark SQL and the Python SDK to do some standard SQL type stuff. I'm going to create a table, create a schema, and I've got my table and schema loaded up as variables here. And then I'm just going to write down simply the data frame. So it's almost like working with Python pandas, but obviously because it's running on Spark, you know, I'm not limited to a single node and the RAM and the CPUs on a single node. This will scale, and this will auto scale to massive volumes of data. So I'm going to write down my delta table into this, which is my catalog schema and table name. And now we get to the fun stuff, right? So this is where the Unifeye team have been talking about some of the new capabilities, as well as the existing capabilities in Databricks. And we talked about H3 indexing, and we talked about the spatial type function. So you'll see these represented as ST underscore, which is kind of an industry standard thing if you're using other cloud-based platforms and lake houses to work with your data. And of course, PostGIS, which is probably the most common spatial database that's open source based on PostgreSQL. So they all have those ST types as well. So this is a pretty kind of standard nomenclature for working with spatial data that Databricks has adopted. So what am I going to do? I'm going to cast those latitude, longitude columns, which exist in my data set at the moment as floats, so like as numbers with long decimal points. I'm going to cast them as a geometry type, so that they're kind of, just think of it as another type in your SQL. You know, you've got your strings, you've got your variant type in Databricks, you've got numeric types, and now you've got spatial types or geometry. So I'm just simply casting my latitude and longitude data using the SQL query. So where you see ST underscore, that's where I'm calling the built-in Databricks SQL spatial types. And there are many types that you can work with. You can work with polygons, you can work with line strings and points. Those are the most common kind of primitives when we're working with spatial data. And here I'm also casting the lat long to H3. So the different resolution levels that we talked about and how that's a great way to index your data and query it in a tabular way. So I've generated all those columns, and I'll just print out to do a quick check that that's working. And this is what my data frame in Delta Lake looks like. I've got my latitude, longitude data, and this is the new spatial types. So I've called it point underscore geom, and this is a point type of geometry data. So this is now, you know, native to Delta Lake, and this is kind of queryable in Databricks. And finally, I'll do a kind of a type check. I'll check that my geometries are all valid, which is one of the functions that's available in Databricks Spatial SQL. And I'll just group by, so I created like a Boolean column on my table, and we can see that if we do a group by all of the records, which is 7.3 million in my current data set, are valid geometry points. So you can see how these functions are actually really useful for data engineering, right? And kind of shifting left on where a lot of enterprises will be pushing spatial data into their cloud platform already. Now they can actually just call those types and put type checking in place effectively, and declare the expectations of those data types early on and to the left of their data pipelines, so that the quality can be assured and maintained, and things can be caught early on. So I'm now going to aggregate my data. I'm going to write down some separate tables with aggregates because I want to do some time series analysis on H3 and on time. So I just write a SQL query to group by the H3 indexes and group by time as well, which gives me a nice kind of aggregate tables to work with. And I'll show you what you can do with that kind of aggregation. This is what the tables would look like. So different H3 resolutions, counting the numbers of hexes, counting the numbers of records, which in our data set represent GPS pings of vessels. So let's kind of visualize that a little bit and bring it to life a bit more. So I'm just going to build a H3 visualization in my notebook, and I'll import a library called PyDeck, which is a great Python wrapper. It's actually based on a JavaScript spatial visualization library called DeckGL, which is one of the best kind of open source visualization libraries out there for visualizing spatial data, and it allows you to use hardware acceleration on your local machine to visualize millions of points or polygons on an interactive map layer, which is obviously great if you're starting to work with spatial data at scale. So here I'm importing the Python wrapper for that. I'm not going to visualize millions of records. I'm just going to group my data by H3 resolution 5. I just want to get like a quick sense check of what the distribution is spatially of my data. So I'm going to generate some aggregates, prep my data for visualization, create a color map using normalized values so that I get a nice skewed distribution of color based on the data. And then I'm going to do some centering of the view state, which is where the map visual is going to be focused on the globe when I spin up my map. And then finally, I will set some other parameters, zoom levels and view state information, and create my interactive visual. So this is, I'm working within a Databricks notebook in this demo example, but it would be very easy to send this or render this as part of a Databricks app, which is a functionality that Databricks offers that effectively allows you to do all the heavy lifting in Databricks and then serve a visual like this, which is interactive, into a kind of web app format and make that exposed to your users, but still using all of the authentication and data governance that comes out of the box with Databricks. But here we're just using a notebook, and we can see the distribution of our data, kind of nice high level view, and it's all centered around the coast. And remember when we had that bounding box showing us this corner, the reason is that these US jurisdiction islands have some data in our data set over there. And up here we have the Salish Sea. And there's a lot of vessel activity here. If I hover over one of these, you can see my aggregate data that I generated, which is the H3 index, the number of unique vessels, and the total records. So I've got a high-level heat map. Let's jump into using some more spatial functions with our data, and perhaps focusing on the Salish Sea. And there's a famous vessel which is pictured here, which is called the Tally-Ho, which is a restored old vessel, which I think dates back centuries, which is the subject of a YouTube channel. We'll share the links afterwards, but it's interesting to track its movements in the AIS data. And of course, we can do that because we have the ability to query the data spatially. So I'm going to load in some libraries in my notebook. I'm going to load some reference data. And one of the most common formats for reference data in the spatial world and GIS world is something called a shapefile. So here I'm loading in a shapefile. A shapefile is just a way of storing spatial data, and it's a very common format that's used, and you can work with that natively in Databricks. So I'm loading in a shapefile which basically looks like this, and it contains properties on the data. The geometry is represented as a binary here, and we're going to convert that, and it's going to give us points that we can map. But we're also interested in all this metadata because it gives us information about each port. So this represents all the ports in the Salish Sea. And what we're going to do is kind of join together the port data with the vessel location data, which obviously has a time series element. And what we can do then is actually quickly build up a data set which gives us information about the journeys of the vessels traveling between the ports. So I'll show you how we can do that very simply with a few queries. Firstly, I'm opening up the ports data set, casting it from JSON format. So converting that shapely into a more tabular standard format here, where you saw before it was nested as JSON in the shapely file. And then I can use a Python library called GeoPandas, which is a really great Swiss Army knife of working with spatial data. Of course, you can use it in Databricks. And I'm just going to visualize those points so I can understand where they lie. And you can see around this Salish Sea, there's all these ports distributed. So let's do some analysis. So if I filter down to particular ports that I'm interested in, I'm going to ignore the small ones. And I'm going to try and connect the dots. And I'm going to join in my AIS data, which, as you can remember, was a few million records. And I'm going to try and understand, of those 7.3 million records, how many of them are actually located close to those ports. So because the ports exist as points, I can use some tooling within our spatial types queries in Databricks SQL to create a buffer around those. So I'm going to use a buffered geometry, and I'm going to use a coordinate reference system to call what's called st_buffer. So think of it as just creating a space around each of those ports, points that represent the ports. And then we'll just try and join those together with the AIS GPS pings to see which vessels were in the vicinity of ports. And we can just do all of that with these native spatial queries. So I'm creating some envelopes around the buffered ports and just creating bounding boxes. And I'm going to filter the events. And finally, I can do what's called a spatial join. So a spatial join is one of the most powerful features that's now available in Spatial SQL in Databricks. And spatial joins famously tend to be quite complex and compute heavy. So they're exactly the type of thing that is well suited to using a lakehouse and a cloud native tooling like this to solve. So when I join my data together, I get the equivalent of a SQL join, but I'm joining spatial types. I'm joining those buffered ports with the point data in my AIS data. And as the Unifeye guys mentioned, this scales really well in Databricks because not only is it running on Spark, but it's optimized using our proprietary query engine as well. So now I'll do some window analysis, and I'll use a function in Spark called window, and I'll partition my vessels and by vessel ID and time. And then I'll actually create little segments in the data, and I'll do some analysis around where the vessels are dwelling in locations. So I'll specify a criteria that says if a vessel is loitering within one of my buffers for 15 minutes, I'll treat that as a journey or a trajectory. And then I'll have a sense of where vessels have started and finished their journeys, and I can fill in the gaps and then quickly build up some analysis around arrival time and departure time. So now I actually have a different kind of data set that gives me some meaningful BI, MI about my vessels and where they've been going to and from, and of course the time series element of that. And then I can start to aggregate that and look at counting of the journeys and so on. And so in this example, we have the origin port, the destination port, and the count. And we're able to kind of, make sense of and almost like tabulate or flatten what is, quite difficult to work with in its raw form. So as I mentioned, all of this demo that I've made available today is available in this Git repo. So feel free to clone this and run it. You will need a Databricks workspace. If you don't have a Databricks workspace, Databricks has launched free edition. So you can actually if you just Google Databricks free edition, you can go and spin up your own free version. It's limited in credits, but it's free for life, and the credits will reset every 24 hours. So that's a great kind of sandbox to play around with Databricks tooling. And this particular repo uses something called an asset bundle in Databricks. And an asset bundle is basically infrastructure as code. And on the back end, it's using Terraform. But there's no Terraform in this repo. And if you click into this YAML file, you'll see it contains all of the information in human readable form that is needed to actually run this end-to-end in any Databricks workspace. And what does that look like? If I can just share my screen back to the, finally share something else. Yeah, so I'm just going to quickly jump into VS Code. So this is my local IDE, and I've got my Git repo cloned, right? I've got my code here, and that contains the notebooks that we just walked through, as well as some pipelines and jobs that created the data. So using the Databricks CLI tool, which is easy to install, and authenticating to my Databricks workspace, I'm just going to type Databricks bundle, which is how we work with asset bundles in the CLI. And I'm just going to deploy the bundle. And because I'm working within the context of my Git repo, Databricks CLI is looking for that YAML file. So the YAML file is what makes it a bundle. There's nothing kind of special going on here. There's no Terraform code to be written. It's just going to deploy that bundle, and it's going to build a Python library. And I can actually run that as well. So typically a bundle might contain a job, which in Databricks is just a series of tasks. It might be Python, it might be SQL. It might be spinning up an app or even a dashboard. So a lot of the things in Databricks can be controlled through asset bundles. And finally, if I jump back to my Databricks UI, so I'm going to just jump very quickly back into the UI, and I'm going to show you from the jobs and pipelines view, that job that I just triggered, you'll see is now running as a task. And so I've kind of launched that. And if we click into the specific run of this job, we can see that job running. So it's now downloading the AIS data. And then after that's done successfully, it will decompress those files. And you can see how, in Databricks, you can kind of chain together jobs and tasks and workflows, either through the GUI or programmatically working in your preferred IDE. That's the end of my segment. So I think I'm handing over now.
Yep, don't mind. Thank you very much.
Thank you very much, Josh. We are going to continue with Felt and hand over to Hasnat.
Just give me 1 second. Just give me a second. I think I need to quit and reopen to share. So hold on.
Sarah, can you make me the presenter and I will put the slides?
Done.
Okay, is Hasnat back? If not, I will cover the content.
Sorry, I'm back.
Okay, I'm sharing the screen. Please do the presentation. I will move across the slides.
Cool. All right. Right, give me a second. Right. So yeah, I'm Hassan. I'm a senior data engineer at Unifeye, and yeah, across my experiences, I worked a lot with dashboards like Power BI, Tableau, even some custom dashboards in like HTML, JavaScript libraries and whatnot. And a lot of times it's we have to plot a lot of regional data. And like as we mentioned before, a few weeks ago, we went over to the Databricks office and we got to work with some geospatial data. And towards the end of it, we got to use a new platform called Felt, which is, plotting geospatial data. On to the next slide, please. So yeah, what is Felt? So it's a new modern solution to geomapping. It's quick to use, it's visually aiding, and integrates really well with AI. And it brings a very quick ease of connection to data. So it connects well with Databricks. So you can connect to SQL servers, you can connect to Postgres, Databricks especially. But if your connector isn't available, you can use the API that it comes with. So I think the name of the game here is to make it quick, and with Felt you can get going really, really quickly. And I think a lot of times when you use these solutions, they might be like they might require a lot of setup, which in this case you just don't need much setup at all. Go to the next one. Yeah, so the name of the game here is to get things done in seconds. It's generally possible to get started in seconds. I've tried and it does work. So it's very simple to get started, and I recommend anyone, if they do have any data or they just want to play around with it, open up a trial account, get some CSV data, whether it's your data or something you can find online. There's a lot of data on ONS or any governmental data does exist. And you can easily just drag and drop it in and it will work. It will do something straight away for you. But with that easy learning curve, you have a well thought out tool set. So, you have dynamic legends. It's a web platform, so you can open on your iPad, your iPhone, any mobile device, or just your desktop. And it has great collaborative tools and access controls. On to the next one. So yeah, the reason this is a great tool, as Databricks partners, we want to enable the most out of our clients' data. And I think Felt brings out that value for their data. And it doesn't matter who you are. You can be an analyst, you can be a data engineer, you can be a GIS professional, you might just be a business user, you just might want to see something. So it serves many stakeholders throughout the spectrum. Personally, for me, I've been using it recently to analyze my raw data. When you get a lot of raw data in, it's hard to make sense of what that data is, and just being able to open on a map allows you to understand what needs to be analyzed, what needs to be processed, and whatnot. So yeah, main thing is that it's accessible, small learning curve, but it does have those advanced feature sets that if you did want to do some more advanced things on it as a GIS professional, you can do that. On to the next. So yeah, so with Databricks, Databricks has a new AI-driven approach, and it's recently announced Agentbricks, Mosaic AI, and a bunch of other AI tools. So, and with these tools, it takes away the clunkiness of integrating AI, and it just is seamless AI integration, which brings value to your data straight away. So yeah, we've seen this being demoed with Agentbricks, which is coming out soon. But in Felt, you can also do the same thing. You can give it your data, and from that, you can just ask a question. It'll build a script for you, and you can plot that data straight away. So it's fairly quick. And when we say we want to get things done quick, this is the way. You don't even need to write a script for your data. You can just put your data in and get something out of it. And moving on, business users get to build apps within minutes. That is very true. I think a lot of systems require a lot of setup. As soon as your data is connected, it's very quick to get going. So you can get something going in minutes. And that moves on to the next point, where for enterprises is great. If you can do something quick, if you can scale it, get stories across, get your narrative across with your data, we're basically making moves with our data. But yeah, I'll take over share access because I do have a demo. I think someone needs to. Cool. Everyone can see my screen. Nice. So for the purpose of this demo, we'll make it quick because we've only got 10 minutes. We are using the Renewable Energy Planning Database. So the reason I use this is because it's free data. If you want to try it, you can go use it. It's a CSV file. And what I did is download that. So what this data represents is renewable energy projects that are in development. And it also includes renewable energy projects that already exist. So we can calculate things like what energy we're producing and whatnot, what's being planned, what already exists. So there's a lot we can do with this data. But there's not that many rows. It's about 4,000 to 5,000 rows. So if you want to get going, this is probably a good place to start. So yeah, I just took this data into Databricks, did some processing, nothing too important here. Going back to what Jordan mentioned earlier, Databricks does have spatial SQL functions to translate coordinates. So a lot of the data that you might get from government websites are in the British National Grid system, and you will need to convert it. So that's all I've done here is create some data here, and we create another aggregate of data that we can plot again. So what I'm going to do in this demo is to show you how quickly we can get going. So I'm going to start fresh, and we're going to get going straight away. So right, here we are. So we're in Felt right now, and we're going to start fresh. So we're going to create a new map, and we will get something simple like this. I'm going to go for this dark layout just because it's better on the eyes. What we do is we go to upload anything, and as you can see, we have a bunch of options. So you can upload a CSV file, Excel file, or you can connect to a data source. So Databricks is here, but if you are using any of these, you can. So for this setup, you will need an SQL warehouse in Databricks and a service principal. But don't worry about this. There is a guide just here as to how to connect to it. It literally took me about 10 minutes to set it up. And I do recommend using the machine-to-machine authentication. So yeah, I already have my data uploaded. And you just click on your data. This is coming directly from Databricks, and you just press create layer. All right, so this does take about a minute or two, but for demo purposes, I'm just going to open one up that has the data in already. So as soon as you open that, this is what you'll get. It's because it has longitude and latitude data, it will plot it straight away. And I think, okay, let's do something with this data. So for this demo, my goal is to see what projects are currently active, and we just want to look at the categories across the UK. So I've seen this data, so I do understand it a little bit more. So what I will do is I would add a filter, and I'll just say development status is a column here. There's a few here like abandoned. You can see there's a few, and we just want to go with operational. There's a two here. Might be one might have a space and one might not. Select those two, and we can see that we have about 3,000 features. So right, we can just see across the UK there's a good set of projects going on. Some national trust areas don't have anything going on, but that makes sense. Okay, but still we're not getting anything out of this data, we're not understanding anything. So what we can do is go to style, we can create a category, and we'll do it by technology type. And already we can see, okay, we can show something. We can see up north. Is someone speaking? I'll carry on. Yeah, we can see up north we have a lot of these wind onshore projects going on. And then down south, as is a bit more sunnier, we have a lot more of the solar projects going on. So yeah, Cornwall has a lot going on, South Wales. That makes sense. Cool. So let's do something else. Let's add like a stat. We want to know something general about the information that we got going up. So we can add a stat here. We can choose something, choose our data. Let's do a sum of the megawatts that it's producing across the UK. Yeah, that's right, total megawatt. There we go. Straight away we can see we get a number. We got about 53,500 megawatts electricity of total capacity. This is what the UK can potentially produce right now. And then if we want to like create like a dynamic legend, we can just do that. We can go, let's do something by region. Cool. So again, we can see we have like this bar chart here. So if we click on Scotland, we can see okay, Scotland's got the most going on. The Southwest also has a lot going on. But yeah, straight away, we've been able to, in just in about a few minutes, create something that tells us the total amount of megawatts we can get in the UK and what each region of the UK is producing. So I had some time earlier to kind of create this map. This took me a few minutes, and I just wanted to understand throughout the UK what points, which one of these projects are creating a lot of electricity. And then we can see here, there's a lot of these offshore projects. So we have this offshore project here, this one here, and you can see both of these alone create more than all of Lincolnshire. So yeah, this is just a quick insight into our data. So on to another demo. We talked about AI, so seamless AI integrations. So there's a tool in Felt where you can just ask it a question and it will plot it for you. And to me, it's fairly amazing. So I'm going to ask it a question like, create a layer where I can see all planned, because we already had the operational one before, planned projects, let's say in Wales. So we will ask the question, it will go away and create a SQL query. And if you're in a situation where you don't want to write a query and you need to get something out really quick, you just need to understand something, you can just use this tool. And this will take a few seconds. It will give us a preview of the data and then we can plot it straight away. And this shouldn't take too long. Let's try that again. All right, this isn't working. Maybe the AI is not working. But I did do it earlier. I asked the question, create a layer where I can see all planned projects in Wales. So it's the same query. And I can just go on, create the layer. And that will take a few seconds and it will plot it for us straight away.
Since we are waiting for the map to be processed and to come with the results, I will answer some of the questions that were posted. The first one was, I believe, onto the XML format, and you are converting to comma-separated values files. You should not need to do a conversion to this. You can use the autoloader, has the XML feature in it, and you can create your table and have it as a delta format. So no need to convert it to C. comma-separated values before that. Hassan, do we have the map?
Oh, yeah, we have the map. Yeah, so it just took about a minute. A minute is rare in these demos. But yeah, this just gave us all the planned projects that are happening in Wales. And you can see there's a lot happening in Newport, Cardiff area. But yeah, so this demo kind of showed us how quickly we can get started, what we can plot, and how we can utilize the AI tool within Felt to just plot things for us that we just want to find out straight away. But yeah, I'll leave it here. Thank you very much. Bianca, do you want to answer any more questions?
Yes, so thank you very much for attending today's session. I hope you find it useful and you have took some learnings away and you can play with Databricks, but also with Felt. If that's all right, I will answer some of the questions that were onto the chat. However, please be aware that this session was recorded. I will upload it to YouTube and share the link if you can't stay longer. So one of the questions was around Postgres parity in Databricks. So Databricks now ships native Spatial SQL with geometry and geographic types, and there are over 80 ST functions, such as ST intersects, ST buffer, ST transform. Supports like, but it's not one-to-one, so it's not identical. So there is something different about it, and the coverage isn't complete. You can check the list is available onto the Databricks website. I will add also the link onto the chat. But if you need functions that aren't there, you can also run Apache Sedona or your UDFs on Databricks as a complement, and you will have essentially the same functionality. Regarding the map rendering, Databricks is not a map tile OGC server, so it won't natively expose those endpoints. Use Databricks for the compute storage delta and serve maps through GCS. We can see your email. Hasnat, please stop sharing.
I think someone needs to disable it for me.
Yes, please. So as I said, you can use the Databricks for the compute storage and serve maps through geographical information system server or a web map stack. So you can connect directly to API tools. That's my answer for now. I'm sure that will evolve in time. Using the Geo server with Databricks, so recommended way is to curate the data into Delta, export to GeoParquet on cloud storage, published onto a Geo server. Of course, you can use as per Josh demo. So it's not generic available. The GDPC store. You will need an engineering effort to add that one. I'm not sure if there are further questions. If not, we are going. Sorry?
No further questions.
Okay, thank you very much. Thank you for attending today. We have next week webinar on to Unity Catalog, so please join that one as well. And onto the following week, we have AI and Databricks on Databricks. Of course, we will have a demo as well. Thank you again, and hope you have enjoyed today's session.